Now we want to consider what happens if we, or how we might switch this integral to polar coordinates. The motivation being that the denominator, 16 minus x, square root of 16 minus x squared minus y squared, but the expression 16 minus x squared minus y squared in the denominator is just 16 minus the quantity x squared plus y squared, which is 16 minus the r squared coordinate for polar coordinates, so that this becomes somewhat simpler. To switch the region to polar coordinates, let's first describe the region once more. The region corresponding to this integral is 0 less than or equal to x less than or equal to 4, x going from 0 to 4, and then y going from 0 to the square root of 16. 0 less than or equal to y less than or equal to the square root of, not the square root of 16, but the square root of 16 minus x squared. This region, if we sketch it in the xy plane, and of course if we remember where all this came from, we know what the region is pretty much, but let's just see how we would work from this given integral to the conversion. So in x and y, y equal to the square root of 16 minus x squared is just y squared equals 16 minus x squared, y squared plus x squared equals 16. That's our curve corresponding to this upper limit, so that of course y goes from 0, well, let's not worry about that. This curve is just a circle of radius 4 centered at the origin, and in polar coordinates the region is just r running from 0 to 4, because it's the region within this integral, the region where x runs from 0 to 4, y runs from 0 to the square root of 16 minus x squared. That region is 0 less than or equal to r less than or equal to 4, and theta going from 0 to pi over 2. That is our angular coordinate running from the x direction up to the y direction through the first quadrant. So our integral becomes the integral from 0 to pi over 2 with respect to theta of the integral from 0 to 4 with respect to r, and remember that our area increment is r dr d theta, so the integral would be 4 over the square root of 1 minus r squared, 16 minus r squared. The parentheses might be a little confusing, and I didn't make a great choice. This outer parenthesis here really isn't necessary. Here's our area increment. This is our dA, and we do the integral in this order because the theta integral, there's no theta dependence in anything here or in the limits on the r integral. So we're going to do the r integral first, and then the theta integral is going to be very straightforward. So we can write this perhaps with more coherent grouping as the integral from 0 to pi over 2 of the integral from 0 to 4. And let's factor this 4 out here. I've got room to write that down out here. That being constant factors out of all the integrals. So we have the integral from 0 to 4 of 4 over the square root of 16 minus x squared r dr. This is going to be the integral with respect to r, so all of our r terms have to be represented within this integral. So putting that together, we have r over the square root of 16 minus r squared dr d theta. Now the antiderivative of r over square root of 16 minus r squared is going to be quite straightforward. We can just use a very simple u substitution. Let's let u equal 16 minus r squared, so that du is going to be negative 2r dr, and the r dr we have here is therefore going to be negative 1/2 du. Okay, I've taken a minute to write down this integral and this substitution on a separate sheet of paper. Our rectangular integral has become the polar coordinate integral, and we're into the process of doing the inner integration, the integration with respect to r. We let u equal 16 minus r squared, so that du equals negative 2r dr, and we're just into the mechanics of integration now. So that our r dr, the r dr that exists up here, is just negative 1/2 du, so that our integral becomes 4 times the integral from 0 to pi over 2 with respect to theta of an integral of negative 1/2 du over the square root of u. So that would be negative du over 2 square root of u. Now we could change our limits 0 to 4 on r to the limits what? If r is 0, u is 16, and if r is 4, u is 0. So this could be negative the integral from 16 to 0 du over 2 square root of u. However, we're not going to do that. We're going to just leave our r limits in the integral, but we're going to specify this is a limit from r equals 0 to r equals 4, so we don't mix up these limits with limits on u. It could be done either way, but we're going to keep it this way, and once we find our antiderivative, we're going to express that back in terms of r. Now the antiderivative of this expression with respect to u, first of all, the negative 1/2 can come out. So we have negative 2 instead of 4. We have the integral from 0 to pi over 2, and excuse my hesitation, but I decided right in the middle of that I didn't want to factor out that negative 1/2, so I've changed this back to 4. Okay, my antiderivative of du over the square root of u, well, that's just an antiderivative of u to the negative 1/2. The antiderivative being 2u to the 1/2. So we have what? We have negative 2u to the 1/2. We have 2u to the 1/2 times negative 1/2, which is just negative u to the 1/2, or negative square root of u, evaluated between r equals 0 and r equals 4, and that with respect to theta. So we have 4 times the integral from 0 to pi over 2 of what? Now, negative u to the 1/2, where recall u was 16 minus r squared, becomes the negative square root of u to the 1/2 is the square root of u, so that's a negative square root of 16 minus r squared, evaluated between r equals 0 and r equals 4 with respect to theta. And that's 4 then times the integral from 0 to pi over 2 of what? When r equals 4, this is 0. 16 minus 4 squared is 0. When r equals 0, this is the square root of 16, which is 4. So this quantity is going to be negative of 0 minus 4 with respect to theta, which is just 4 times the integral from 0 to pi over 2 of 4 d theta, which is, okay, that might have been off the bottom of the screen. In any case, the arithmetic here is very simple, so that's 16 times the integral from 0 to pi over 2 of d theta. Antiderivative of d theta is just theta evaluated between 0 and pi over 2. We get pi over 2, so that's 16 times pi over 2, which is 8 pi. Let's recall that this is the surface area of sphere, radius 4 in the first octant. You'll recall from middle and high school geometry that the surface area of a sphere is 4 pi r squared, where r is the radius of the circle. If r equals 4, that gives us an area of 4 pi times 4 squared, 4 squared being 16 times 4 is 64. So the surface area would be 64 pi. There are 8 octants, so 1/8 of 64 pi is 8 pi, so that this result is confirmed by this formula. And in fact, this integral that we've done can be done in terms of general radius, call it radius A. If we replace 16 by A and replace the 4 here and the 4 here by A, we get the general integral for the first octant integral, first octant surface area of the sphere. And when we go through the identical steps, again, just replacing 16 by A squared, 4 here and 4 here by A, we get the formula that the surface area is 4 pi A squared. If A is the area, if A is the radius, then we're going to get 4 pi A squared. So this integral, this process can be adapted just very slightly to give us this general formula.